Now start potential step, part second. In part first, we have considered case first, E greater than V naught in 2 videos, and now we will proceed toward case second, E less than V naught. So what is E and V? Let us consider here. We have this one dimension x, here Vx potential at origin indicated here, x axis, y axis you may take, but this is generally for potential, and here region 1, region 2, draw potential height V naught, this is. So write down here region 1, region 2. So what is shape of potential? Potential shape is this one. Look, this, again drawing by red line for clearance. This is. So this is potential step. In case second, we have E less than, so let this line is for E. It is whatever particle we will take here, its energy will be less than potential height. So now consider particle, this particle. Now when this particle we are considering, it is in motion. So whenever particle is in motion, there is wave packet associated with that, and we can consider about this particle nature using wave nature. As we know that according to de Broglie, for moving particle there is wave associated with that wave, that is wave packet. This moving particle will be treated as wave. So now drawing waves for this. Now these waves will reflect or transmit, that is we are talking about R and T. This R is quantum mechanical reflection coefficient and quantum mechanical transmission coefficient in terms of quantum mechanics. But what we see generally in classical sense, if particle energy is less than height, this potential height, yes, it will reflect. But according to quantum mechanics, we want to see that is there any probability that this particle will approach here, or this wave nature will exist here also. So this is our aim, and we will show this by finding some expression. The description, in this description box you have link for case first, and we are going to continue our case second through this video. For this we will consider wave function psi 1 here and psi 2 here. Now we know that particle motion and in case of quantum mechanics can be studied with the help of Schrodinger wave equation. So we are considering for one dimension. So write for region first Schrodinger wave equation, del square psi 1, because psi 1 here, del x square plus 2m upon h cut square E minus V psi 1 is equal to 0. In case of potential step, it is clear that the value of Vx is 0 here. It is no height of potential, and in case of this region, this is V naught. So for x less than 0, 0, but for x is equal to or greater than 0, this is V naught. Okay. So we will solve for both region first and region second. And as same in case first, we will use boundary condition, continuity equations, and finding Schrodinger wave equations, solution, and probability, current density. So these are again. So for first region V is 0. So this will be reduces to del square psi 1 upon del x square plus k1 square psi 1 is equal to 0. So what is k1? K1 is under root 2me upon h cut. Now consider for region second. Now before this we can take solution for this psi 1. Solution will be a e to the power I k1x plus b e to the power minus I k1x. What actually here? This is incidence wave. So we take for this a e to the power I k1x, and for reflected part we take b e to the power minus I k1x. So these are plane waves. So considering solution this one. So clearly this is incident part towards positive x-axis, this is reflected part towards negative x-axis. Now as same for region second. For region second, del square psi 2 upon del x square plus 2m upon h cut square. Now here this is V naught for region second. So we will write E minus V naught psi 2 is equal to 0. But what is here? We are considering for case second. So for case second, this is, we have to manage it, del square psi 2 upon del x square minus 2m upon h cut square V naught minus C psi 2 is equal to 0. Okay. If you have remember, for case first we considered it for K2, but what is here something different. So we will consider here K2 dash. So writing for this del square psi 2 by del x square for K2 minus K2 dash square psi 2 is equal to 0, and solution will be psi 2x. What we have considered for case first, that was the c e to the power I k2x plus b e to the power minus I k2x, but something different is here. I want to show you more clearly. See first roughly some part. In case first we saw that this solution was I k2x plus d e to the power minus I k2x in case first. Yes, you have must seen that video. So that was for that one when e greater than v naught. for this one when we consider this part as k2 square. But here is something different. So look here, that k2 was under root 2m e minus v naught upon h cut. But what we are considering here k2 dash. This k2 dash is what? This k2 dash is under root 2m v naught minus e upon h cut. Just find relation between these. What is the relation? This will be minus of under root minus 1 2m v naught minus e upon h cut. Yes, obviously this will be I, this will be k2 dash. So what is k2? This is 1, this is k2. So what will be I k2 now? This is minus k2 dash. Now look here, from here this wave function, what will wave function? When we will put I k2 is minus k2 dash, put here. So wave solution for this, we will write c to the power minus k2 dash x plus d to the power k2 dash x. But as we know that there is no reflected part in region second, so this d will be 0. So finally psi 2x will be c to the power minus I k2 dash x. So this is what? Exponentially decreasing solution. Wave functions, but in that case we will have only that one. So something different is here. On the basis of the difference we will get something different result. Okay, so complete wave function. Complete wave function, we know that psi x t psi x e to the power minus I omega t, separation of space and time. So we can write for that also in using this. So psi x t, we have to multiply, this is, we will write upper for psi 1, down for psi 2, we using multiplication of e to the power minus I omega t. So what will be final? A e to the power I kx minus omega t plus b e to the power minus I kx minus omega t, and for psi 2 c e to the power minus k2 dash x and e to the power minus I omega t. So this is complete wave function. Now to what we have psi 1, just we have found that was a e to the power I k1x plus b e to the power minus I k1x, and psi 2 is c e to the power minus k2 dash x. Okay, now look, we will apply for J. What is J? We have introduced it, current density. This is IH cut by 2m. If we will write for transmitted part psi t, then this will be psi dx d by dx of psi t is complex conjugate minus complex conjugate of wave function and this again. So this we have introduced in case first in previous video. Now what is psi tx? Psi t is the transmitted part, incident part, reflected part, transmitted part. This is what transmitted. So psi 2 can be written as psi t. That is, we will put now psi t x. So what we think first, psi t, there is no I, no imaginary quantity. So complex conjugate and this value will be same. So psi t x and psi t star x, both are same. Both are c e to the power minus k2 dash x. So when you will put here, you may see that by finding dy dx of psi tx, or we can say that dy dx of psi t star x, this value will be minus k2 dash c e to the power minus k2 dash x. Now we will put here. After putting, what we get, jt. We want to see what is value of jt. So it will be IH cut by 2m psi tx. This is what? This one, c e to the power minus k2 dash x, and this part is here in multiplication, minus k2 dash c e to the power minus k2 dash x, minus again this part, minus this, putting value using this and this values we will put here, d by dx of this. So again this value minus k2 dash c to the power minus k2 dash x. This is obviously this will give minus minus plus, so this plus minus quantity will be cancel out. So what we get final, jt is 0. Jt is 0, and we know that for transmission coefficient T is equal to jt upon ji. It means that T is also 0, and by definition we know that R plus T is equal to 1. So R is equal to 1. This means there will be reflectance, no transmittance. Now find relation for constant, because we have constant ABC. So let us see. For that we will apply boundary conditions. As we know that psi is continuous function of x as well as its first derivative. So applying boundary conditions. What we see that for psi 1 0 and psi 2 0, and this first derivative psi 1 0 and psi 2 0. So this both condition we will apply and we will see. So for this it is clear that this will what give, we will put here. I want to remind one more thing, that in case first we have used complete wave function in which we have time also, so there was no effect here. Or in first case, what we observe for psi 1 and psi 2x, we can use this one also without any doubt. So using for that, what is the value of psi 1? Psi 1 was what? Psi 1 was a e to the power I k1x plus p e to the power minus I k2x and psi 2 c e to the power minus k2 dash x. So when we put 0, so what we get for equating? Using this relation, we will get a plus b is equal to c, and using this relation we will find differentiation of this and differentiate this one also, putting x is equal to 0. So what we find? I k1, it will be common, I, this is k1, and e to the power I k1x a minus b to the power minus I k1x. This differentiating is equal to minus k2 dash c to the power minus k2 dash x, and we have to put 0 also. Here we have equate d by dx psi 1x and d by dx of psi 2x, but here is what? For continuity, x is equal to 0. So we will put x is equal to 0. So I k1 a minus b is equal to minus k2 dash c. So we have this relation and this relation. Using this relation, we will find a relation between b and a and relation between c and a. For this is also easy one. Find out. This we get a plus b is equal to c, and I k1 a minus b is equal to minus k2 dash c, and we have to use this to find relation between b and a and c and a, so that we can see r and t. Now look, for this calculate a minus b minus k2 dash upon I k1 and c. Just divide this both. On dividing, you will get a plus b, a minus b minus k2 dash upon I k1. Using component or dividend rule, we get 2a by 2b minus k2 dash plus I k1 by minus k2 dash minus I k1 is by plus and minus. Now take this I common, you can take minus I, so we can write as k1 minus I k2 dash by k1 plus I k2 dash. Now write down for b by a. This is for actually b by a. Yes, just reverse here and taking common minus I, you will get the value of b by a is this, and we can find reflectance now. What is reflectance? B by a and b star upon a star. These expressions we have find in case first. So if we have seen case first, no problem will be here. To find complex conjugate, this I here will be plus. So first writing for b by a, k1 minus I k2 dash upon k1 plus I k2 dash, and for b star by a star, we have to take k1, this will be plus I k2 dash upon, and this will be k1 minus I k2 dash. Yes, for complex conjugate. Now multiply this. After multiply, we will get k1 square, and this will be plus k2 square using a plus b and a minus b, that is a square minus b square, and here also we get again k1 square and here also plus k2 dash square. So again look, this is 1. Yes, that is when we seen by using current density we get R1, again using expression we have 1 again. As same we can find relation between C and D. For C and D, look here, we can put the value of B from here to here. So now using this relation for to calculate C by A. So to calculate C by A, write down IK1 A minus B. So A minus, this will be C minus A, so minus C plus A, and yes, obviously minus K2 dash C on RHS. 2 times of I K1A is equal to I, this shift here, I K1 minus K2 dash C. So we have get now C by A, which is 2I K1 by I K1 minus K2 dash. We can take I here, so that this can be written as 2K1 upon K1 plus I K2 dash. So what we have find here, C by A. As same we can find C star by A star. This will be 2K1 upon K1 minus I K2 dash, because for transmission, that is quantum mechanical transmission coefficient, we will write T is equal to C by A and C star by A star. Better to find a probability density, because we have already R plus 3 is equal to 1. So okay, finding a relative probability density. This is, yes, psi t square. This is what, mod c square e to the power minus 2 k2 dash x, because we know that the value of psi t is psi 2 is equal to c e to the power minus k2 dash x. We have expression, this is square of it. So C and C star will be mod C square, and this is okay. Now putting the value of C square, so when we multiply here, multiply these two terms, so this will be C by A, this is square 4k1 square upon k1 square plus k2 square, this is 4 dash. So we get this, shift this a square here. So what we get 4k1 square mod a square upon k1 square plus k2 dash square e to the power minus 2 k2 dash x. This is, as x is large, this falls exponentially to small. So what we observe that classically there is no transmission, that is none of the particle will found in x greater than 0, that is for second reason. But according to quantum mechanics there is non-zero probability. We can see a short diagram. What we have found in a figure like this part, region first, region second, this was a potential V naught, and drawing here waves of energy less than V naught, that is E, and here we have taken waves. So what is important? Important this one. Now this wave will decrease exponentially, because we have seen that the value of psi 2 is c to the power minus k2 dash x, and we have relative probability density, that is for second reason. We are solving for psi t. So for psi t we are considering about transmission. It means that according to quantum mechanics we get transmission also, which is not the case in case of classical sense. So what we have, this is what we have differentiate between classical and quantum mechanics. Thank you.